Hi everyone, my name is Marina Vance. I go by Nina. I'm at the University of Colorado in Boulder. And today I'm here to talk to you about the need for collaborative field studies in indoor chemistry and indoor quality in general. By collaboration, we can reach a lot more. We can probe a lot deeper into the science, and we hopefully will have more findings to share with the scientific community. So I have one example of a large collaborative field study that we led last year called HOMEChem. So before I talk about HOMEChem, I'd like to bring up a little bit of history. There have been previous collaborative indoor air field campaigns, some very large ones. We are not the first ones. We are standing in the shoulders of giants here. So there are three studies that I'd like to highlight. The first one is the TEAM study funded by EPA. They followed 650 people in 4 states, and they looked at their personal exposures to about 20 VOCs. And it happened in the late 70s, early 80s. And then about 15 years after that, the RIOPA study investigated 100 US homes in 3 states, and they looked at indoor-outdoor relationships of volatile organic compounds and PM2.5. And then about 10 years after that, there's a study in Europe called Office Air. They investigated 37 office buildings in 8 European countries. And again, they were looking at these indoor-outdoor relationships of VOCs, particulate matter composition, and more. So there's something that is in common if you think about these big studies, right? They try to look at many buildings, as many as they could, and they were looking at a few particular species, chemical species of interest or indoor pollutants of interest, because obviously you can't look at everything everywhere all the time, right? So you have to make a choice. And their choice was to look at as many buildings as possible to try to be as representative as they could of cities or countries or states. So their focus was on indoor sources of air pollutants, but also the penetration of outdoor air pollutants. The study that I'm going to talk to you about today is sort of the flip opposite of that. So our study used one house, so we try to keep that one house constant, and we try to investigate as many chemical species as we possibly could. We try to measure everything that we could. Our focus was, again, still on indoor sources, penetration of outdoor air pollutants, but beyond that, we try to probe deeper into the fundamental chemical and reactions, the physical mechanisms, the transformations that are going on indoors, and hopefully that level of fundamental science can be translated to other homes as well. So this is our study. It's called HOMEChem. It stands for House Observations of Microbial and Environmental Chemistry. The study took place in Austin, Texas last summer, so around May, June of 2018. We had a pretty detailed investigation in indoor chemistry, as detailed as we could possibly make it at the time. With over 30 state-of-the-art instruments. We had over 20 faculty members from 13 universities in the US and in Canada. We also had some industrial and governmental partners joining the study, loaning us instrumentation and their expertise. So we ended up with over 60 researchers on site. At this point, I'd like to acknowledge my co-principal investigator. She's Professor Delphine Farmer from Colorado State University in the Department of Chemistry. And you can see at the bottom there the logo of all the institutions that were collaborating with us on site. So as I mentioned, the different thing that we did from previous collaborative studies is that we chose one home. So we picked very carefully what home we were going to use, and the home we chose was the UT Austin Test House, or the U Test House. This house was operated by Professor Attila Novoselak at UT Austin. I'd like to acknowledge his hard work during this campaign. And this house is a research instrument. So nobody lives in this house. It wasn't built for a living. It was built as a research instrument. And UT Austin has had that house for over 10 years. It was actually purchased through an IGERT fund that Dr. Corsi led over 10 years ago. And since then, the house has been intensely characterized and used for building efficiency and indoor quality studies. So for us, it felt like a really good place to have our study since the home had already been characterized so well. So the home has several HVAC systems that we could choose from, continuous outdoor air supply, and also monitoring of temperatures on surfaces and in different rooms. Energy consumption was also very, very well monitored, so it was a very good candidate for our study. So now I'd like to present to you a little bit of the instrumentation and the level of collaboration we had in the study by using this wonderful photo from our open house day. Not everybody's in the photo, of course, but everybody that was there that day is in the photo. And I'm not going to get into details of the instruments, but I'll show you sort of the breadth of the analyses. So we had several teams measuring aerosol physics, so size distributions, concentrations of particles, and their dynamics over time, ranging from 1 nanometer to 20 microns, different locations around the house. And you can see the logos of the institutions that were collaborating on bringing their instrumentation. When it comes to aerosol chemistry, so the composition of particles, we also had a variety of aerosol mass spectrometers in the study, including the Goldstein group, with the same instrumentation that Alan just presented before. We also had measurements, of course, of volatile organic compounds with a variety of mass spectrometers from different institutions. And finally, we also had measurements of oxidants and other trace gas compounds. And finally, measurements on surfaces in the microbiome. So these teams were actually the only offline teams in the campaign. They came over and they took swabs of all of the surfaces, brought them back to their labs to evaluate both the chemistry and try to understand the microbiome of the house. So that gives you a little bit of flavor for HOMEChem in terms of instrumentation. But I'd like to talk a little bit about the experimental design as well. So I mentioned this is a field study. Usually in a field study, you go out into the world and you try to see the reality of what's going on without interfering much. But in our case, we had a little bit of both. So we couldn't really dictate outdoor pollution and how much is coming into the house. We can't really control the home. It's not a glass, a box. So we couldn't control those things, but we could control the types of activities that were performed. So we had a very clear activity schedule, and we were trying to take as many notes as possible on what was being performed at any given time. And we chose 3 categories of perturbation that are hopefully activities you all perform in your home on a daily basis. So we try to focus on cooking, cleaning, and occupation and the use of personal care products. As Alan mentioned before, that's also, human occupancy plays a big role in their chemistry. So we wanted to probe into that as well. We had 2 different types of experiments. The first, we call them sequential. So basically, we're repeating the same activity over and over, trying to get as many replicates as we could. And another kind that to me was a little bit more interesting, we call them layered activities. So a more realistic representation of our home. Volunteers would come in, cook breakfast, and they would clean a little bit, and then cook lunch, clean a little bit, and then cook dinner. So maybe this is a much cleaner home than an average home who cleans their house twice a day. But at the end of the day, we were trying to watch for that interplay of emissions throughout the day in a more realistic fashion. So at the end of the day, we wonder if this is really a field study that's really well controlled, or if we have a more realistic chamber study. We're sort of in between that. So basically, we had a very busy day. What you see here is our experimental schedule. We're swimming in data right now. The experiment only happened a year ago, and a lot of these measurement techniques take a long time to calibrate and go through the data. So we're still working on that. But today, I'll show you a little bit of data from one of the 4 stir fries we cooked on June 17. So what you see here is a time series. So on the x-axis is time. On the y-axis is number concentration of particles. Number, not number. So what you see here is the concentration of particles of all sizes, ranging from 0.1 microns to 20 microns in size. And you can't really see much beyond the pink line, and that's because all the lines are collapsed. That means that on a number basis, all the particles we observed indoors, over 99% of the particles, are below 100 nanometers in size. These particles are very important from a health perspective, of course. We understand they can travel deeper into the respiratory tract, and some of them can translocate into other organs, get into the bloodstream. So from a health perspective, they're very important. Now let's look at the same data from the same day at the same time, but on a mass basis. Now that pink line that I showed you is collapsed to the bottom. So on a mass basis, those ultrafine particles that are very important for health don't really represent much in terms of mass, right, in this particular scenario. What you see here is the mass contribution of particles. So while we're cooking the rice, before you saw a bunch of ultrafine or sub-100 nanometer particles, now we don't see them anymore. And then what you really see is increase in particle mass loadings when we added vegetables to the oil and then when we added the sauce. And these particles range broadly in size, from 0.5 micrometers, the blue line, all the way up to 20 microns, the biggest, the green line. And that's consistent with previous data that shows that when you're cooking with an open pot with frequent stirring happening all the time, all of that bubbling leads to the formation of larger particles. But there's really a broad range here on a mass basis. So now if we zoom in and only look at PM1, so particles 1 micrometer in size or smaller, we can actually take a look at the data from Professor Peter DiCarlo at Drexel University, who is here today, and look at the data from his aerosol mass spectrometer, and then we can see a chemical fingerprint of those particles. So the AMS spectrum here is showing mostly the green regions, which are similar to oleic acid, or they did some comparisons between that and just splashing the pan with oil, and found that the signal that they're observing on a mass basis is really mostly coming from the oil. You can still correlate them to when the veggies were added to the oil and when the sauce was added, but the fragments detected by the AMS mostly had CH and CHO groups. Now, if we zoom in a little bit more and try to look at just at the bottom of that chart, you can see that there's a little bit more going on. When we add the food, there's actually emissions of organic nitrogen-containing compounds associated to the food. There's also a little bit of chlorine and other things that you can see, and you can tie those because this is a time-resolved measurement. You can time those with the activities that were going on at the time, adding the vegetables, adding the sauce, for example. So that was just a little bit of the kind of information that we're getting from this study, just to give you a flavor. Some of the preliminary results we've observed so far from HOMEChem were, of course, related to high emissions of particulate matter. So I focused on particulate matter today, even though we had also VOC measurements and other things. What we observed was that the use of the propane, in our case it was a propane oven and stove, was the main source for ultrafine particulate matter, less than 100 nanometers in size. The food was the main source for fine particulate matter, unless there's a lot of stirring going on, like in the case of the stir fry, then you can get all the way up to coarse particulate matter. Occupant movements was the main source of coarse particulate matter, because as we're walking, we're resuspending dust from the ground, we're shedding particles and skin cells from our own bodies. We are also observing a lot of interesting chemical reactions that take place during cooking activities. We're still probing into those data, and what a lot of results are showing is that the surfaces around the house throughout that month-long period of activities was evolving and changing as their pollutants were depositing onto them. The final message that I'd like to leave with you today is that we understand our pollution processes much better outdoors than we do indoors. These questions are still pretty open-ended, and even with the wealth of data that we've collected at HOMEChem, what we're finding is it's opening up new questions, answering some, but opening up many others. So it's important to look at the indoor environment. As was mentioned before, we live indoors and we spend a very significant amount of time in our own homes where we are introducing all of these chemical reactions ourselves. So with that, I'd like to acknowledge funding from the Alfred P. Sloan Foundation for this study, our massive team of collaborators, and I'd like to mention our network, indoorchem.org. If you're curious about indoor chemistry, please visit our website. We have descriptions of all the projects that are related to this group, and we also have a pretty healthy Twitter account that shares the latest papers that have been published and blog posts and things like that. So I welcome you all to join the community there. Thank you.